Good evening and welcome to our sixth lecture under our series of classes in statistics for the social sciences. As usual, Emostita is my name and I welcome you to this class. Now, in this class, we shall be talking about a very, very important statistical concept known as correlation. But before we proceed further, here is a quote by Mark Redfield, gotten from Brainy Code. He said, "You are trying too hard to find a correlation here. You don't know these people. You don't know what they intended. You tried to compare statistics and correlate them to a result that amounts to nothing more than speculation." That's Mark Redfield. So I think that's a food for thought for you. Try and ponder deeply and see if you can make sense out of this quote. Now, in today's class, like I said, we shall be talking about correlation. And here is a brief summary of our course outline for today. So we shall discuss what correlation is. We shall also discuss the two most popular, correlation calculation formula, that is the Pearson product moment correlation, and then the Spearman's rank correlation coefficient. We shall also talk about linear regression, and we shall also see how you can do all these calculations for the Pearson product moment and the Spearman's rank correlation coefficient. We shall also try briefly to see how we can use Excel, Microsoft Excel, to calculate the statistical measure, and also see how we can use the software to plot what we call the scatter diagram that shows us the relationship between two variables and how they are correlated with each other. So without much ado, let's go straight to our lesson. Now basically, when you hear the word correlation in statistics, the first thing that should come to your mind is the word relationship. And basically, correlation is a statistical measure that expresses the extent to which two variables are linearly related, meaning they change together at a constant rate. And it happens to be a common tool for describing simple relationships without making a statement about cause and effect. Now, generally speaking, simple correlation and simple linear regression coefficient actually may be subdivided into 5 general types as regards the value and sign or direction of such coefficients. But before we go deeper into that, I think in the next slide it will be important and necessary for us to define some very, very important terminologies that will help us fully understand this subject. Now, because in correlation and linear regression studies, we often make use of two important terminologies known as the dependent and the independent variable. And generally, the independent variable is the variable that, mathematically speaking, is being represented by the letter x and actually lies along the x-axis in our xy plane, while the dependent variable is represented by y and lies on the vertical axis. Now, a very important thing we need to know is that for any given study, how do we determine the variable that is independent and the one that is the dependent variable. Now, one way to determine the variable is from the point of view of causality, in other words, cause and effect. So let's pick a typical example. Suppose you want to carry out a study concerning the contamination, or rather the air pollution for a given city, considering the number of cars that you have in that city. So in other words, you can see here we have contamination or pollution, and here the number of cars. Now in this case, For you to be able to know which one is dependent variable and which one is the independent variable, you simply ask the question, what is the cause and what is the effect? Now you can see that in the case of the cause of the pollution is actually the numbers of cars that are plying the road. Now, the number of cars that are plying the roads, in other words, it means the more the number of cars you have, the more the contamination will be. The lesser the number of cars, the lesser the contamination will be. So in other words, the cost in this case, which is the number or the quantity of cars that are plying the city, is the independent variable, while the effect, which is the contamination or the pollution that will be experienced in that city, is actually the dependent variable. Another classic example is when you want to carry out a study concerning the grades that students obtain in a particular course vis-a-vis the number of hours that such student dedicates to their study. And in this case, you can see that the grades obtained, whether an A, B, C, or an F, is dependent on the number of hours that the student dedicates to his or her study. So in this case, the independent variable, which is the number of hours, happens to be the cost, while the dependent variable, which is the effect, happens to be the grade. So as you can see quickly here, I said the dependent variable is actually assumed to be the effect, and it is the variable that the researcher studies, which varies according to the changes that occur in the independent variable, while the independent variable is actually assumed as the cause for which changes in a phenomenon or situations are supposed to occur. So therefore, when you want to determine which is the dependent variable and which is the independent variable, all we need to do is just for us to ask the following question: what is the cause? Once we are able to determine the cause, then the cause is the independent variable. And then the second question is, what is the effect? Once we are able to determine the effect happens to be the dependent variable. So these two definitions are actually key in carrying out regression and correlation studies. So let's commit that to heart. Now let's make progress. Now, just like I said before, generally correlation and linear regression may be divided into 5 general types as regards the value and sign or direction of such coefficients. And it is important for me here to stress the difference between correlation and linear regression. Now, linear regression actually helps to establish the relationship between two variables, that's x and y, which is the dependent and the independent variable, while correlation helps to tell us the strength of these association or relationship. So usually linear regression helps to express the relationship in a mathematical form, while correlation helps to tell us the direction and the extent of these relationship, whether it's strongly related or loosely related, or there's no relationship existing at all. Now, the first type of relationship is usually if you collect your census data, that is your dependent and independent variable, and you happen to plot them as a paired data point, and you have your data points aligned in a perfectly straight line such that your points appear exactly on this line. In other words, you have a perfect straight line. Now, the relationship in this kind of graph indicates or implies that we have a positive, direct, and perfect relationship. So in other words, the value of our correlation coefficient here R is equal to plus 1. And here we say we have a perfect estimation of prediction. And it is important to take note that all plots actually lies along a straight line. Now, but before I proceed, it is important to know that the correlation coefficient R is actually a value that lies between -1 to +1. And if I have a straight line here, here is +1 and here is -1. So in other words, you can see -1 So in other words, when you calculate the value of R must lie between -1 to +1. So in other words, if your value of R is, let's say, around this region, very close to 1, then we say that the two variables are strongly positively linearly correlated. And if the value of R is much more closer to -1, we say there's a strong negative linear correlation. And of course, if the value of R is 0 or close to 0, we say that the two variables are not linearly correlated. In other words, there's no relationship existing between the two variables, that is the dependent and the independent variables. Now, the second type of relationship is when you plot your graph and it happens that you have a graph that looks like this. Now, if you have something like this, if you have something like this in such a way that when you plot your graph, only a few parts of your data points actually cut the straight line, but you also have some other data points that are evenly divided between your straight line, then in this case, we said that the relationship is positive and direct, but actually non-perfect. So in other words, the value of your correlation R is less than plus 1.0. Though it is not perfectly 1.0, but it is close to 1.0, but less than that. So you can see that all plots are not on the same line, but a discernible trend can actually be seen here, that there's a roughly linear correlation or relationship existing between these two variables. Now, the next scenario you can have is when you have your data points in this format. Now you can see that this very particular straight line graph is the opposite of this that I've just highlighted. You can see here the relationship is negative and indirect, and it's also non-perfect. In other words, in this case, we can see that our R, the value of R, is less than 0 in this case. So we say that the relationship is negative and indirect and non-perfect in this case. Now let's make progress. Now the last but not the least type of relationship is something of this form. Now you can see that if we attempt to draw a straight line here, if we attempt to draw a straight line here, you can see that here there is no any discernible, pattern. In other words, the data on this very particular plot are scattered, and the interpretation is that there is no any, readily discernible trend that could be seen here. And in this case, we said that there is zero or approximately zero relationship. In other words, the value of our R is equal to 0 in this case. So basically, these are the various scenarios that you could have whenever you are carrying out an investigation between two bivariate data, and you want to see the relationship that exists between these two data, and then the direction and even the strength of their association. Now let's make progress. So just like I said, basically there are different kinds of correlation plots, but the two most popular ones that we shall be discussing in this lecture is one, the Pearson product moment formula, and then the second one is the Spearman rank correlation coefficient, and we shall see how each and every one of these is being calculated. So later I shall switch on to my Excel worksheet and then show a demonstration on how all these data, these values could be calculated. Now, as can be seen from this slide, the Pearson formula is actually given as shown here. Now, it is important for us to take note of the definition of all the terms in this formula. So it's given denoted by R is equals to N multiplied by the summation of xy multiplied by the summation of x multiplied by the summation of y divided by the square root of n multiplied by x squared minus the summation of x squared multiplied by the summation of y squared minus the summation of y all squared. Now it is important for us to always take note. So it then means that for us to be able to calculate the Pearson R, each of these terms will need to be determined. The product of xy, the sum of x, the sum of y, the sum of x squared, the sum of x, all these will need to be determined. And I'm going to show a demo using our Microsoft Excel spreadsheet. So you can see the definition of all of these variables here. N refers to the number of pair of sample to data that we are studying. Sigma denotes the sum of all the indicated elements. Summation x implies the sum of all values of x. Summation x indicates that each value of x should be squared first before being added. So we should take note of the difference between summation x squared, and summation x all squared. All these values are different, and you need to be very careful while doing the computation in order not to run into error. Where R represents the linear correlation coefficient for the sample data, and then when we make use of rho, stands for the linear correlation for a population of paired data. So R and rho stands for the same thing, only that this is for sample, and then here is when we are considering population. So we need to take note of this. Now, at this point, I'm going to share my screen, my Excel spreadsheet, and then let's see how all these values could actually be calculated. All right. Now, but before I proceed with the calculation of the Pearson, R, I will also want to show us how to plot our scattered diagram, because it is the scattered diagram that actually helps us to see the nature of the relationship, whether there is a perfect positive correlation or a perfect negative correlation or no correlation at all. Then before we can now go ahead to calculate the Pearson R. Now here I have a table that shows the temperature in degrees Celsius for 12 days in a particular city, and the amount of sales, in dollars that an ice cream company makes for 12 days, depending on the temperature of that city. Of course, it should be expected that the higher the temperature, or the higher will be the sales, because hotter temperatures will actually place a demand for people to want to lick ice cream. So the first thing is that we are going to draw a scattered diagram and see. And it's always important for you to put your independent variable on the first row if you want to represent your data in the horizontal format, and then the dependent variable on the second row. But of course, if you want to do that vertically, then of course your independent variable should occupy to the first column, while the dependent variable should occupy to the second column with their proper heading. So you can see these are the various temperatures. For the first day, the temperature was 14.2 degrees Celsius, and a sales of $215 was made. When the temperature was 16.4, a sales of $325 was made, and so on and so forth. So for us to draw our scatter plot, the first thing you need to do is for you to highlight all the data that you intend to plot. And this is what I'm going to do. I'm going to click from the first box where temperature is, and then highlight all my data that I intend to plot. And then I go to my insert on the command menu of my command button. I click on insert, and then of course I come to charts under the charts group, and then click on charts. And then you can see here under the subclass I click on scatter. Now as soon as I click on scatter, Excel automatically insert a scatter plot with all the plots being represented as dots, as you can see. And you can see that here I have the temperature, which is the independent variable on my x-axis, and the cells, which is the dependent variable on my vertical or y-axis. Now the next thing I need to do is just for me to tweak this diagram a little. So you can see that both the x and the y-axis start at a point 0. Now, but of course, our temperature, the minimum value of our temperature here is 14.2. So I'm going to tweak. I'm going to place my cursor on the x-axis, click, and then right-click and go to Format Axis. And from the menu that I have, I can see that under the axis options, I have my bounds minimum. So in the case of the minimum here, I'm going to put 14.2. I put 14.2 as my minimum, and then click out, and then you'll see that the x-axis has neatly adjusted. And then here I also come to my vertical axis, right click on that, and go to format axis. Then under the minimum, I will also look at the cells and see what is the minimum cell. The minimum sales was is $215. So I can put 215 here and then click out. And of course, you can see that my chart has been neatly readjusted. My chart has been neatly readjusted. And if I want now, I think I can also add labels to my chart. So I click on the chart and come to this plus symbol, which indicates chart element. And then I check on axis title. And then of course, under the axis title, I can type my cells here. And then I come to the horizontal axis and also edit. Here I put temperature. Okay, and then under the chart title, I can put a very befitting title if I want. Graph of sales versus temperature if I want. So you can see a scatter plot has been easily inserted for me here. And of course, if I want, I can also include a trend line. I still click on the chart and click on this chart element and add a trend line here. So by clicking on this, you can see it has neatly drawn the line of best fit between all the points that are within this XY plane. So you can see here now, this is how to draw a scatter plot. Now I'm going to switch to the next page in my Excel, and then we are going to see how we can calculate the Pearson R mathematically and traditionally, and then later we'll see how we can use this Excel spreadsheet induce function in order to calculate the Pearson R. Now you can see here on this table, we've been given a table of 3 employees, just 3 employees, and the number of years they spent in a particular company, and then the number of mistakes committed by each of the employees. So you can see here the first employee spent 4 years in the organization, and when he was observed, let's say within a year or month, it was observed that he has committed 10 mistakes. The second employee spent 2 years in that company, he has spent 20 years. The third employee spent 3 years and he has committed 12 mistakes. And then we want to see how we can calculate if there is a correlation or a relationship between the number of mistakes committed vis-a-vis the number of years spent at the company. Now, don't forget, while we are talking on our PowerPoint slide, this is the formula for calculating the Pearson R. Now, all we need to do is just for us to add additional columns so that we will be able to calculate our XY, summation of X squared, and Y squared. And that was what I neatly did here. So you can see the number of years spent at the company is represented by X, the number of mistakes represented by Y. Then I now have another column for X squared. And how do I do that? It simply means each of these values of X, I simply square them. So you can see here that X squared is going to be equal to 16. So, but let me just quickly use Excel mathematical ability or functions to do that. So I'm simply going to put equals to, then I click on the first value, and then I raise it to the power of 2, and I press my enter key, and it gives me 16. Now for me to get the other values, all I need to do is to click from the bottom right hand corner of cell D3, and then drag, and Excel automatically calculates that. So you can see here that 2 squared is 4 and 3 squared is 9. The same thing for y squared. I simply put equal sign. I click on cell C3, then I raise that to the power of 2, and I press enter. You can see 10 squared is 100, and for me to get the other values, I also click and drag. And then the last but not the least column is the product of x and y. In other words, 4 multiplied by 10 will give you 40, 2 multiplied by 20 will give you 40, and so on and so forth. So I simply put equals to x multiplied by y. If you press your enter key, that gives you 40, and then you can also click and drag to get. Now the next thing we need to do is for us to find all the sum, because from the formula we also need to know what is the sum of x. And here the sum of x is going to be equal to, and to simply put my SUM sum, and then I show it all the data whose sum I want to calculate, and I press my enter key. Now in the case of sum of 1, I do the same thing, SUM. I add all these values, and I press my enter key, and Excel neatly sum this up. So let's see, the summation of all the x squared is also going to be equal to SUM. Excel has neatly given me that. For this, it's also going to be SUM. And then last but not the least, so you can see Excel has neatly inserted all these formulas for me. Now the next thing we need to do is for us to come to our formula. And our formula says R is equal to N multiplied by sum of. So you can see that our N in this case is 3, because we only have 3 employees, multiplied by the sum of XY, and the sum of multiplied by the sum of XY. The sum of XY in this case is 116. You can see 116 minus the sum of X, which is Y, multiplied by the sum of Y, which is 42. You can see 42 here. Everything divided by the square root of N. Our N is 3 multiplied by the sum of X squared. The sum of X squared is 29. You can see 29 here, minus sum of X squared, which is 9. You can see 9 here, multiplied by N, which is 3, times sum of Y squared, which is 644, minus sum of Y squared, which is 42. So, and if you do the math neatly, you should obtain that R is equals to minus 0.94. Now, and the interpretation of this is that, do not forget we said that the value of R usually lies between minus 1 to plus 1. You can see that this one is very, very close to minus 1, meaning that the two variables which is the number of years spent in the organization, vis-a-vis the numbers of mistakes or errors committed, are strongly negatively correlated. In other words, it means the higher the number of years of experience, the lower the number of errors or mistakes committed. And that's how we interpret that. Now, the Excel has an inbuilt, Pearson function, which you can use straight away without going through this, except if otherwise you have been asked to show all your works. And that is the Pearson function. And basically, this is how you do that. I will simply, so I'm going to place my result here, and then simply type equals to, and I type the word Pearson, and then of course, the Pearson function brings out this, that I should enter my first array of data, and my first array of data is going to be the years of experience. So I'm going to click from 4 to 3, and then I put a comma, and then input the second array, which is the number of mistakes or errors committed. So I will click from 10 to 12, and then of course I close my bracket. And the moment I press my enter key, Excel automatically returns the Pearson R for me, and here, as you can see, it has given me the answer of minus 0.9449, which is exactly the same thing as this. But actually, as a standard, convention, Pearson product moment are usually rounded up to 3 significant figures. So you can see, basically, this is how we calculate the Pearson product moment. Now I'm going to switch back to the first chart, my correlation chart, or the scatter plot, and also see how we can calculate. We'll simply just go ahead and calculate the Pearson R using the Excel inbuilt function. So as usual, I type my Pearson and then also supply the range of data. So the first one, the first array is going to be my temperature, which are all the values in these boxes. And then I put my enter key and then click the second variable, which are the cells, and then close and then press my enter key. You can see in this case, I have a value of 0.9575, which is very, very close to +1. In other words, it simply implies that these two variables, temperature and cells, are strongly positively linearly correlated. In other words, the higher the temperature of the city, the higher the cells. And of course, if you look through your data, you can see that is what this very particular value is indicating. You can see when the temperature was 14.2, the sales of $215 was made. But when the sales was 18.5, which is higher than 14.2, sales of $406 was made. So you can see how important all these statistical measures help us to analyze bivariate relationship between two data. Now permit me at this point to switch back to my Excel spreadsheet. I'm in a PowerPoint so that we can continue with the Spearman rank correlation coefficient. Now, it is important to know that the Spearman rank correlation coefficient is the non-parametric version of the Pearson product moment, and it's also represented by the Greek letter rho. Also, we can represent it by R suffix S. But in the case of the Spearman rank correlation coefficient, it measures the strength and the direction of a monotonic association between two rank variables. So the first thing is that it is the non-parametric version, and it doesn't assume data distribution, while in the case of the Pearson, we assumed that the data that you are investigating are normally distributed data. Also, in the case of the Spearman, we make use of ranked variables. So let's quickly see how we calculate that. And basically, we have two formulas depending on whether our data, when we are ranking our data, we have a tie, or our data do not have a tie. And the formula to use when they are tie is rho is equal to 1 minus 6 summation d subscript I squared all over n into n squared minus 1. While in the case of when there are no tie, this is the formula we use. Now let's quickly go straight ahead and calculate an example. Now you can see in this case we have been given a table of the scores obtained by students in two subjects, that's English and mathematics. And you can see here, let's see how many students do you have here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are all the scores scored in English, and these are the scores scored in mathematics. Now, since we said that the Spearman ranks actually made use of the ranking of the data, all we need to do is just for us to include another column, that is the ranking for English and the ranking for math. So in other words, we are going to assign a ranking of who is the highest. So you can see for English, 80 happens to be the highest score, and of course, we've given it a ranking of 1. 76 happens to be the second highest score. It has a ranking of 2. 75 is the third, a ranking of 3, and so on and so forth. The same also applies to the ranking of mathematics. Now, the next thing you do is for us to find the difference between these two rankings. So hence, we insert a third column, the difference. So you can see that the ranking for English here is 9, while that of math is 4. So you find the difference. 9 minus 4 gives you a 5. Here, 3 minus 2 gives you a 1. 10 minus 10 gives you a 0, and so on and so forth. And then the last but not the least column is for you to find the squares of the difference of the ranking. So in this case, you can see that 5 squared will give you 25, 1 squared will give you 1, 0 squared gives you 0, 3 squared, 9, and so on and so forth. Now, once you obtain all this data, all you need to do is just for you to neatly plug in all this data into your formula. So, and the first thing we did was for us to find the summation of d subscript I squared, which is the summation of all these values that we have, 25 plus 1 up to 1. And this was exactly what we did here. And then the next thing we do is we substitute this value into the main equation with other information as follows. So you can see here, this is our formula that we've been given. So we now have 1 minus 6 multiplied by the summation of the subscript I squared is 54, hence we have 54, divided by n, that's the number of our samples data, is 10, into n squared, that is 10 squared minus 1. And of course, if you do the math, this is what you are going to have. Now, it is also important for us to know that the Spearman rank correlation coefficient is actually an approximation of the Pearson product moment. So you can see, as n is equal to 10, hence we have that our rho, or R sub S, is 0.67. And this indicates a strong positive relationship between the ranks individuals obtain in the math and English exam. That is, the higher you are ranked in mathematics, the higher you rank in English also, and vice versa. So that is how this Spearman rank correlation coefficient is being calculated. Now, basically, how do you report that? So here we said how you report the Spearman correlation coefficient depends on whether or not you have determined the statistical significance of the coefficient. If you have simply run the Spearman correlation without any statistical significance test, you are able to simply state the value of the coefficient as follows. In other words, you have rho is equal to the coefficient, or R sub S equals coefficient, e.g. rho equals 0.67 as we obtained, or R sub 3S equals 0.67. So this is how you just write it statistically. That is, if you have not carried out any statistical significance test. However, if you've run a statistical significance test, you need to include some more information as shown below. So in other words, rho, and then with what we call the degree of freedom. You need to also include the degree of freedom in this case. So you can see here we have rho of h, that's the degree of freedom, is equal to 0.67, and p is equal to 0.033. So basically, this is how you carry out correlation analysis in statistics. But before we take our leave, permit me to share the open class question in the next slide, and then we call it a day. Now the first open class question says, the first open class question the first one states that differentiate between correlation differentiate between correlation and simple linear regression. And I will suggest here that you should simply do the differentiation in a tabular form. Put a table, correlation on the left hand side and linear regression on the right hand side, and simply highlight the differences between them. And then the second question says, is Pearson sensitive? Is Pearson product moment sensitive to outliers? And then the last but not the least says, those correlation implies causation. In other words, when two variables are correlated, does it imply that one causes the other? Yes or no? And then explain a little further. So I think we've come to the end of this class, and I hope that the lecture and the information I've presented here has been very, very informative, and I would like to thank you for viewing. See you next week, and I encourage you to answer your open class questions and do some other activities and upload them in the relevant section of the learning management system, and also take note of the deadline. Until then, it's bye-bye from me. See you next week.